Hello. Today we're going to start looking at doing proofs using trig identities. So trig identities are a bunch of algebraic and mathematical rules involving our trigonometric ratios like sine, cos, tan, and our reciprocal ratios, cosecant, secant, and cotangent. Before we get too far into it, there's one important notation piece that we're going to see today that we haven't really seen before. And we see it actually in the first question here. It's this sine squared theta, and what that means. So one of the things with this trigonometric notation with sine, cos, etc. is when we square, it's a little ambiguous. So there's a bit of a peculiar notation where we write, for example, sine squared and then our angle. And what this means is that the entire function of sine theta is being squared. So that's equivalent to something like this, which means that it's a repetitive multiplication of sine theta. So that'd be sine theta times sine theta. Okay. Now, that's a little non-intuitive. Normally, we would think that we might instead have written it like sine theta squared. That's kind of what our intuition would say. The issue is that what is meant by this is sine of theta squared. Oops, not the bracket there. So that's where the angle is squared first, and then we plug it into sine. Okay, so there's a difference. In this one, we calculate sine of the angle, and then we square the result. And in this one, we calculate the square of the angle, and then we sine the result. Okay, so this notation, whenever you see the squared on the sine, it means the entire thing is being squared. Okay, so let's start looking at proofs. So whenever we're trying to prove something mathematically in this unit, we always need to be careful, and we need to work with each side independently. So we always split each side. And work on it independently. Okay, so in this question, we want to prove that sine squared theta times cosecant theta is equal to 1 over cosecant theta. Right? That's not an intuitive thing that these are the same. They don't look the same. So we're going to try to algebraically show that they are indeed equivalent. So we're going to split up each side. To do that, we'll draw a vertical line down the center of our page. We're going to say the left side, LS, left side is equal to, and then we'll write out our question, sine squared theta times cosecant theta. So these are multiplying. We'll put some brackets around those if we'd like. And we'll work on the right side. Equals 1 over cosecant theta. All right. So how are we going to show these are equivalent? So one of the first things we'll do in all of our questions is we're going to rewrite everything in sines and cosines. Okay, so that's our tip. I'm going to write that as a tip off to the side. It's not always absolutely necessary, but it often makes it a lot easier. So rewrite everything in sine and cos. And you might be thinking, what about tan? We'll talk about tan later. Okay, so if we take a look at our left side here, sine's already in sine, it's sine squared, but cosecant I can rewrite, and cosecant is one of our reciprocal trig ratios. Cosecant is 1 over sine, so we can rewrite this as sine squared theta times Cosecant theta we can replace with 1 over sine theta. Those are equivalent expressions. All right, and now we can kind of see, oh, I think I could simplify this from here, right? So I have like sine a squared term over itself, right? So we could think of this as like x squared over x. It's the same idea. So we can simplify that. We can cancel the squared, cancel 1 to 1. So cancel the squared with the sine. Cancel one of the signs on the top with one of the signs on the bottom. And we get sine theta. And nothing really strikes me out as obvious to simplify from there, so we'll just leave it. Okay, let's look at the other side. Maybe we can do some work there. We haven't replaced it with sines and cosines yet, so now that I'm looking at this, though, I think if I replace this with 1 over sine, I'm going to have a 3-layered fraction, 1 over sine, and that's really confusing. So a trick whenever you're in a situation where if you do a substitution like this, you're going to plug a fraction into a fraction, and you're going to get a 3-layered fraction. We want to avoid that. It's too much. So what we're going to do is we're going to write a fraction as division, because that's what a fraction really is. So we're going to write this as 1 divided by cosecant theta. And now let's replace it in 1 divided by 1 over sine theta. And now we're dividing fractions. We know how to divide fractions, right? So if you're dividing fractions, you flip the second fraction and change it to multiplication. So 1 times sine theta over 1. And, well, that's just 1 times sine theta, 1 times 1. So it's just sine theta. And now we can see that both the left side and the right side are equivalent to sine theta. So they must be the same. So as our concluding statement, we're just going to write that. They're the same. So therefore, left side equals right side. Okay, this is the general process we're going to follow for all of these questions. We're going to split the proof into the left side, the right side, work on each independently with the goal of getting to some step in our process where they both are equivalent. Usually we're trying to simplify or something like that, and we're trying to show that the left side and the right side are the same. Okay. So there's 3 general things we can do when we're working on these problems. The first is we can replace an expression with an equivalent one. So we actually already did this, right? So we said that cosecant theta is equal to 1 over sine theta. And secant theta we could also replace with 1 over cos theta. We could also do something, we could do cotan is 1 over tan. We'll talk about tan in a little bit though, so I'm not going to write that one down here. But we can also do things like if I have a 1, like the number 1, I could write that as sine theta over theta if I wanted to, right? Because that's equivalent. Or cos theta over cos theta. Or of course I could do secant or cotangent or tan over tan, all those things. But sine and cosine is usually what we're trying to work in, right? So this is another option. Okay. So some other things we can do is we can always add 0. And I put 0 in quotes there because we've seen this step before, actually. When we do completing the square, we do something like plus 9 minus 9. And essentially, we're adding nothing. We aren't really changing the expression. We're just adding some complexity to it that kind of cancels itself out. And then we can do some algebra from there. Okay, we aren't going to do that in trig identities so much, but the other one we will do more so, and that's multiply by 1. So we can always multiply by anything that's equivalent to 1. So we can multiply by sine over sine, or cos over cos, or x over x, things like that, right? So we do that often when we're finding common denominators for adding fractions and stuff like that. And we can also cancel expressions. So we saw that in our first example. We canceled out a sign from the top and a sign from the bottom. The rules for canceling are the same as they were when we did rational functions. So when everything on the top is multiplying, we can cancel top and bottom. All right, so let's see another example. Okay, so this time we want to prove that sine squared over cosine squared is equal to sine x times secant x over cosecant x. All right, so let's split this up into our two halves. So our left side equals sine squared x over cos x. And my right side is sine x times secant x over cosecant x. Okay. Now let's try to look at each side and see if we can simplify it. So sine squared over cos squared, everything's in sines and cosines. I don't really see a way we can simplify that simply by like canceling anything out. Like can't do sine over cosine, doesn't cancel or anything. So I think that one's maybe as simple as it can get. But let's look at the right side. I see some opportunities over here with secant and cosecant to replace them with sines and cosines. So once again, we have, if we replace secant with 1 over cos and cosecant with 1 over sine, we're going to have this like crazy fraction with like 4 levels on it. And that's way too much. So let's write it as a division instead. So secant, we can replace 1 over cosine, cos x, divided by cosecant, which is 1 over sine. All right. And we have a division of fractions, so we'll flip the second one and multiply. So let's see that. So we have sine x times 1 over cos x. We don't flip the first fraction, we flip the second, times sine x over 1. Okay, so here we have a whole bunch of things multiplying, and we have a sine x times 1. Right, we can think of this as sine x over 1 as well. So we have sine x times 1 times sine x. Well, that's sine squared x. Remember, when we write the squared on the sine, it means that we have a sine x times a sine x. And on the bottom, we have 1 times cos x times 1. And that is just 1. Sorry, that's just cos x. And would you look at that? We have sine squared x on the right side and the left side. And we can write, therefore, that they are equivalent. Left side equals right side. We have proven that these two trigonometric expressions are equivalent. Okay. Now, there's a new trig identity. So a trig identity is like a fundamental piece. Okay, so the one that we're going to learn today is tan of an angle is equal to sine over cosine of that angle. Okay, so this is something we're going to memorize. And with our reciprocal trig ratios, we have cosecant and secant as kind of things we can swap in. So if we see a secant, we can replace it with 1 over cosine. We see a cosecant, we can replace it with 1 over sine. When we see a tan, we can replace it with sine over cos. And that's why we don't, that's why we try to translate everything to represent everything in sines and cosines. It makes it a lot easier to work with because we can get rid of tan by making it into sine over cosine. And this also implies we can do something with cotan as well. So cotan is the reciprocal of tan, so it gives us the reciprocal of what tan gives us. Instead of sine over cosine, it gives us cosine theta over sine theta. So if we see a tan or a cot, we can replace them with sines and cosines as well. So our first kind of step that we want to try to do still holds. We want to replace everything with sines and cosines. Let's see an example using this new identity. Okay, so we want to prove that tan x plus 1 is equal to sine x plus cos x, all divided by cos x. Those don't look similar at all, but let's see what we can do. So we'll set our left side equal to tan x plus 1. And our right side equals sine x plus cos x all divided by cos x. Okay, so should definitely replace this tan first. We want to write everything in sines and cosines. The right side's already in sines and cosines. So sine x over cos x plus 1. So the 1 we could write in sines and cosines as well, and maybe we will, but I don't know, do I want that to be sine over sine or cos over cos? Now that I see this, maybe there is something we could do there. So at this point, I think there's two different things you could notice to try to go further. I think the easiest one to notice is the one I'll do on paper here, is that here we have a fraction plus something else, and if I wanted to add these, they would need common denominators. So maybe let's try that. So if I make 1 into cos x over cos x, then I'm adding fractions. Maybe that will help. Sine x over cos x plus cos x over cos x, or cos x over cos x is equivalent to 1, and now we have common denominators, so we can combine these fractions. We'll finish that up in a second, but another way you could have approached this is we can actually split up a fraction that looks like this. So we can rewrite this as sine x over cos x plus cos x over cos x. We can like uncombine the fractions, and we could have kind of approached the same thing. But let's finish this up here. So we combine our fractions, we get a singular cos x on the bottom, and on the top we get sine x plus cos x. So the right side was one fraction, and now the left side's also one fraction by getting common denominators. And we can see that these are now the same. So the left side and the right side are equivalent. So we say, therefore, left side equals right side. All right. So there's a couple more practice questions for you to work on the rest of the pages.